Good afternoon, everyone. Welcome to the second class of the Advanced Topics on Intelligent Data Analysis. Today, it's a pleasure of having several people here in the room. And we have the pleasure of having here today Dr. Allan Tucker from the Brunel University London, and since Professor Pedro Rodrigues know him very well, I would like to pass the presentation, brief presentation.
Okay.
So Pedro,
Well,
please.
Good afternoon, everybody. So this is what we have been talking about for this class, is try to get more people involved with external groups, and fortunately, Dr. Allan Tucker is here, not only himself to give this presentation, but two other colleagues, Howard and Yelena, who I had the pleasure to meet earlier. And of course, Dr. Allan Tucker is a great acquaintance of mine for a long time. Of course, what I can say of him, I should better let him present himself. Otherwise, I would say something that perhaps he wouldn't want me to say. But of course, Dr. Allan Tucker is head of the Intelligent Data Analysis Group at Brunel University London, and he's been in several projects in the healthcare area and the application of artificial intelligence in not only in healthcare, in other areas also, but perhaps from those areas he could talk a little bit himself about them. And hopefully this seminar will be a very nice sparkle to all interactions that we can have later on. So thank you, Alan, thank you, Howard and Yelena, for being here.
So yes, thank you, Pedro, for inviting us, although I think I invited myself. Technically.
No, technically, yeah.
And I've done it again in September.
Yeah.
So yeah, as Pedro says, I'm Allan Tucker. I head the IDA group in Brunel University in London. What I want to talk to you about today is actually 3 separate projects which have all come from the same sort of collaboration that we have with the MHRA in the UK. So the MHRA, I'd never heard of until I started collaboration with them, but because of the pandemic, it's in the news in the UK almost daily. It's the equivalent of the European medical regulatory authorities. So vaccines and whatever else have to be approved through them. Okay, but what I want to do first of all is just give you an idea of where we're from, what we do as a group before I start talking about some of these projects. So Brunel University is named after Isambard Kingdom Brunel. There's a statue of him on the right there. He was an industrialist, he was an engineer, built some of the first railways, first tunnels under rivers. He tried to build the Channel Tunnel to France, but gave up halfway through, but built some of the key engineering infrastructure within the UK many, many years ago in the 1800s. So we were named after him. So a lot of the work at Brunel is led by engineering problems. You can see we're based just in London. So there's a red pin there. The blue motorway around it is kind of the real boundary of London, but it means we have lots of countryside nearby, as well as a metro station that takes you into the centre. Okay, the IDA group is quite old. It was founded in '95 by Professor Xiaohui Liu. And the key with IDA, it's different from just artificial intelligence. It's different from data mining, because it's not just trying to press a button and get an answer. It's trying to be interactive. So the algorithms we design are supposed to work with the experts or with the people analysing the data to try to elicit knowledge. It's not about black box models that do it all for you. We have lots of applications, not just health and biomedicine, but also with the environment, engineering, and even education. And we have a nice website and annual meetings. So some of the stuff, just in a broad sense, the sorts of things we do, as I said, are about trying to build these interactive algorithms. So a lot of stuff involves visualizations or algorithms that create some sort of language that experts can work with. And a really successful collaboration has been with Moorfields Eye Hospital. I spoke here a few years ago about in more detail, and we were interested in building trajectories through the data space from healthy or from young people through to different advanced disease stages or elderly patients. So trying to build these pseudo-times, pseudo-temporal trajectories from data that isn't always temporal. So trying to construct pseudo-time series. And we've had lots of success with trying to understand subcategories of eye disease, like glaucoma, and how it actually seems to impact different people in very different ways. Lots of our work has been involved with building spatial and temporal models of data like this. We also work with biological systems. When the IDA group first started, it was incredibly fashionable to work with gene expression data. We did lots of stuff on building gene regulatory networks, like the stuff you see here. We explored how different diseases, for example, muscular dystrophy, differed between different species. And we managed to find certain key regulatory pathways, which seem to be common between species as diverse as fruit fly, mice, and humans, which allowed them to actually narrow down some of the more fundamental regulatory aspects of the disease. But we also work with other things like plants. So this is a wheat regulatory network, and being able to identify particular parts of the network that are responsible for things like heat stress or drought sort of scenarios. And we work with the environment too. So we're working with the Royal Botanical Gardens at Kew, where they have lots of specimen plant data, so squashed plants, which are ideal for deep learning and image analysis. Work with governments around the Baltic Sea and the North Sea, trying to understand species interactions. So really diverse. But what we do with all of these different diverse applications is use them as a driver for discovering new theories or new algorithms that can actually cut across those different applications. So often we develop an algorithm for one particular problem and see how it actually crosses over quite nicely to a completely different domain. And that's a nice feature really of being able to work with all these different fascinating data sets. So we do have new theories that we've developed as a result of this, things like the pseudo-time, some of the consensus learning algorithms, some explainable deep learning approaches we've been working on. So lots of the stuff always has some sort of applied nature at first, and then is turned into some sort of theory. So that's a kind of flavour, some of the stuff we do within the IDA group. But now I'm going to focus, thankfully for you all, because this is what you're here to hear about, is AI and IDA in healthcare. And as you all know, we've seen a lot of hype about what AI can do for us. We see companies like IBM, like DeepMind or Google DeepMind, making claims about what we can do with medical data using these state-of-the-art AI algorithms. So by using AI-type technology to analyze the data, we want to find ways to improve diagnosis and treatment. Okay, but the key here is that medical data. And we left the EU, okay, I'm sure you all remember that. It's had a pandemic since then, but we've left the EU. We're still under the auspices of the GDPR for now. It's being updated, I think, in the EU and at the UK, so this is where our paths maybe diverge slightly, but we still have to obey these regulations and the legislation. And there's a lot in this that actually has major impacts on AI research. So things like automated processing that is done and used to make a decision about someone, whether it's healthcare, whether it's giving them a loan, anything like this, that person has the right to obtain an explanation about that decision and to challenge it. Now that has major impacts. What's an explanation? Do we have to provide, an explanation equivalent to if a human had made the decision? This is still quite open questions, and GDPR is a fantastic starting point for potential changes and adaptations to that, but it means it will shape how AI research progresses. So as a result of GDPR, but actually a long time before it too in the UK, it was incredibly controversial, as it is in most countries throughout the world, the idea of releasing patient data. We attempted to do it in 2014, a project called Care.Data. It collapsed. The media picked up on this. What? Releasing all of the private patients' data It's unacceptable, clamour, it got louder and louder, and it was canned about a month before it was supposed to go live. They then tried it in the depths of the pandemic to sneak this out, that they were going to do this. So this is December 2019, risks a repeat of the care.data. It actually got to a week of this being allowed to happen, of releasing this. You had to actively opt out. Newspapers got hold of it last minute, a week before it was supposed to go live, it was canned again. So they've realised this is not going to happen in the near future, and we have to come up with ways, whether it's regulation or whether it's technology, to be able to exploit this vast amount of healthcare data that we have, but without releasing it and releasing all the privacy problems associated with it. So the MHRA approached me 3-4 years ago and suggested the idea of synthetic data as a solution. So can we use the real data, the gold standard data, and do something with that to build synthetic simulations of that data? And there's different ways of doing that. We can just add noise in different ways or jitter to the data. And there's also different important concepts to do with synthetic data. So K-anonymization. And this is the idea that if you remove a person, or you key attributes about people, or you generalize at the right level, so it could be, instead of including age, you include people over, you just say they're over 60 or under 60, then you can actually create an anonymous enough data set to be able to do something useful with it. But it's not easy, deciding at what level you aggregate or what attributes you're willing to remove. Another important concept is differential privacy. And this is the idea of, if you remove an individual from an analysis, it should have no impact on the analysis. So if you take that one person out, you end up with the same result. Because if you don't, that means that one individual is identifiable by the analysis itself. And this creates a real problem, this balance of wanting to actually do useful analysis that's personalized medicine, but at the same time not being able to identify a person from the analysis, and it's pulling in two different directions. So bearing all of that in mind, we decided to avoid the idea of adding noise and many of these concepts, and to go down the route of generative models. So building an underlying model of the ground truth data, which we could then sample from in different ways. And there's lots of AI technology out there for building generative models. Probably one of the most famous at the moment, incredibly fashionable, are the GANs. These are deep learning approaches, neural network-based approaches to build data, simulated data, where you have a discriminator that's trying to do some sort of diagnosis or classification in competition with a generator that's trying to create difficult to classify examples. Now, if you look in the literature, you see a lot of differing results from using these sorts of approaches. What we've typically found from exploring the literature is deep learning is not great on categorical data. Okay, it's fantastic for continuous values for images, but for categorical data, it's still quite problematic. And most of our data, it's not all categorical, but there's a lot of categorical data in health records. So we didn't go down the GANs modeling approach. For another reason is GANs are famously black box models, goes against the ethos of the IDA group, though we have deep learning exploration within the group. So we decided not to go down this route. We would go down the probabilistic graphical model approach. Now, these families of models are very flexible in what they can model. So categorical, continuous data, no problem. You end up with a model that has this nice graphical display that's associated with it. Now, you have to be careful how you interpret those graphical representations of data. They represent conditional independencies, which are not always easy to grasp. They use probabilities to model the data, which are certainly easier than embeddings and weights within a deep learning approach. But most importantly, they're interactive. So you can query these models. You can enter information and say, well, what if this patient is over 60? And what if they have high high risk of a particular disease, and see what impacts that has on other variables within the network. You can also do lots of the standard things. So you can have a class node and build a machine learning classifier. You can have a hidden node and make that into a clustering problem. You can extend the models over time, build something called a dynamic Bayesian network to model time series, and hidden latent variables as well to do lots of other interesting unmeasured effects modeling. So really flexible and relatively transparent. So we were happy to go down this route. So we've explored many different approaches to building large-scale graphical models of our primary care data that we hold within the UK government's national database. And we published some stuff. We weren't the first to do this. So Proof Bayes is another similar approach to what we're trying to do, using probabilistic graphical models to build these underlying data sets. One of the key differences that we've exploited is the idea of latent variables within our modeling approach. So we know that we've measured lots of stuff about the population in the UK, but there's stuff that's not measured there. So we use some classic algorithms, the FCI algorithm, which will identify the most likely locations of those latent variables, and then we can try to parameterize them. So this gives us a much better fit to the data sets. It starts to make it a little bit more black boxy because we don't know what those latent variables mean. But in fact, we do end up with much higher fidelity models that seem to fit the underlying population much better. Here's an example of one of the smaller networks we used to build some simulated data. You can see we have 6 latent variables in there. And a model that we can actually query. In fact, we used models like this and worked with GPs to look for potential problem relationships that we know shouldn't be in there, and ones that may have been missed that should be there. So it allowed us to interact a bit and fine tune the models before we started generating simulated data. And then what we did was we did lots of statistical tests on that data compared to the original ground truth data sets. So we looked at distributions, we looked at correlations, we looked at partial correlations, we looked at multivariate distributions. And the general finding was the latent variables dramatically improved the fits. So we ended up with much higher fidelity distributions and correlational structures than if we hadn't used them. So the MHRA and all of the people working with us were very happy with these data sets. We did lots of other tests, but we also knew that we still had something we didn't understand. So the latent variables are still an open question for us. And this is something that we still would like to explore. So the meaning of those latent variables. And by performing these what-if questions, so using inference within the graphical models, we can start to try to understand potentially what some of those latent variables may mean. Now, this might mean some subcategory of disease or some subcategory of people with different responses to medication. It could mean anything. So it's not straightforward, but this is something that we are currently trying to get some funding to explore in more detail. We've also extended it into the time domain. So we explored using just mimic data where we have classical sort of things like ECG and EEG signals to see if the same approach works there. So can we build, like using models of state space time series models, probabilistic graphical models again, but in the time domain to build similar signals to the time series. And in fact, when we start to explore the statistics again, but this time looking at the dynamics, we find very good fits. So we have the idea of an autocorrelation function and a cross-correlation function. The middle graph there shows our simulated autocorrelation function against the ground truth for systolic blood pressure. And you can see it's not a perfect fit. There's actually a bit of a skew there. This is likely to be because the order of the model was not, we weren't modeling enough temporal lag within it. Whereas the cross-correlation function was fantastic. It was almost overlaid the diagonal. So we were very pleased with how this does potentially extend into the time domain. And then what we did with our simulated data sets was say, okay, well, how can we use these? And the real reason the MHRA wanted to release some of these simulated data sets was so that universities and the tech sector could potentially build new apps, new tools to do diagnosis and test them. You know, they couldn't test it on real patient data because we wouldn't give it to them, but they could test it on these data sets and develop it using these data sets before they would be submitted for approval from the MHRA. And we found lots of things like the ROC curve analysis and the precision recall was really good. Not identical, sometimes there were slight biases, but they were good enough to allow companies, so we worked with several companies to see if it allowed them to develop models that were good enough to then go ahead for us to assess them using gold standard data. And they were. We were really pleased about that. But then we got scared, we got paranoid, we were going, okay, we've released this data, but could people still identify interesting things potentially about individuals from the simulated data? So we started simulating, you know, a malicious attack. So for example, let's say a hacker knows an individual, they may know certain things about them already, they know their age, whether they smoke or not, their gender, where they live. Could they use certain bits of information like that to then link it using the simulated data that they got hold of to a potential individual? So for example, if you've got some outliers here, could you say, well, actually this simulated data point here was mostly based on a small cluster of individuals and therefore infer something about them using the simulated data. And what we generally found was there was a risk, it was relatively small, and it was small enough to convince the MHRA that this was a risk that, you know, that you could have with releasing any information about anything. It was aggregated and at a high enough level to allow them to release some small data sets, first of all. So they have done. They released in 2020 a synthetic COVID data set based on that point 1.5 waves that had hit the UK and a cardiovascular disease data set. They've been updating these regularly. So we now have full COVID data sets. I think it was released last month, pretty much all of the waves that have hit the UK. And we've been doing lots of tests on this data as well to try to understand if it captures all of the complexities of the real COVID data. So it's been a massive success, really. The MHRA were really pleased with the fact that they could start to release this data. And it's going on. So we're trying to release many other disease-based data sets using this approach. And then you must have seen in the news, suddenly it was becoming a major concern, the idea about potential prejudice and bias within AI algorithms as a result of data sets that were inherently biased and prejudiced in how they've been collected or what they've been used. This person on the left, have you heard of Dr. Timnit? She worked for Google. I think she was their ethics guru, making sure that whatever they did wasn't evil, which was their catchphrase at the time. They long got rid of that. She highlighted, she thought they were breaking quite a lot of moral codes, and so they sacked her. Probably not the best response. So she then became this renegade who has been speaking out against some of the big companies and small companies and how they're using AI that's clearly making prejudiced decisions. So we sat there as a group with the MHRA saying, you know, we've got the National Care Service data set in the UK. It's huge. It can't be biased. Well, actually, whilst we've got almost everyone in the UK included in there, of course, there are biases. You know, there's societal biases. There's the biases that you'll find anyway when you're doing secondary data analysis. There's diagnosis biases in society. So, you know, GPs may actually have inherent biases themselves in the decisions they make. So there's lots of different reasons why there could be biases, even in a really comprehensive data set. So we need to deal with these potential biases within our simulated data sets, because we're not sure where we would stand if we were to learn a model then generate synthetic data from that model where we know that there are biases in there. That's slightly different than releasing a real data set where there happen to be biases in there, because it means we've actually put those biases in there. So we're not sure where we would sit legally with doing this. So it's helped the fact that we have graphical models and we can look and inspect for problematic relationships, but it's not the end of the story. So, new project. Can we explore the potential of bias within synthetic data set production? And so there's different types. There's spurious correlations, undersampling, clearly for certain subgroups within the UK population, proxies for prejudice. So it could be that a decision's made, and the reason is it's where someone lives. And where that person lives, that postcode is a proxy for ethnicity or age or many other sort of potentials for bias. And the labels themselves. So it could be that a diagnosis is fine and those labels fit the diagnosis correctly for everyone except a subgroup, but the diagnoses are much flakier, problematic. So we have to deal with all of these and we can't pretend that we'll be able to straight away. But one thing we knew we should be able to identify is undersampling. And there's already quite a few techniques for trying to deal with undersampling. So all of the boosting methods, smoked being a famous example, Addersides, smoked fair, all trying to deal with underrepresented cases to improve a classification accuracy. Okay, so you boost through oversampling a minority class, or you undersample one where there's far too many, so you create a more balanced data set. Or you simulate data sets that seem to fill in the gaps, where you don't have a lot of data for that region for a particular classification. Now, that's not really what we want to do. We're trying to get rid of the biases in our data set so that we better represent the UK population. We're not just trying to make it closer to 50-50 if it's a binary decision. So we're not trying to do exactly the same thing as smoked and some of those approaches. So we came up with a different approach. We're not trying to simply create balanced classes. We're trying to identify which communities within the UK are underrepresented for particular diseases. We're quite lucky because we have this Bayesian network synthetic data generator. So we're not just going to use some distribution to generate, then we're going to use this complex joint distribution represented by this complex synthetic data generator. So we've got an advantage already by using that. So essentially what we would do is we would use some standard uncertainty analysis to identify which cases were more uncertain when we were classifying them. Because when we use these probabilistic approaches, you end up with a probability, a distribution of whether someone may have a disease or not. And we can use that uncertainty to identify the cases within our data set that are more problematic. And therefore, we can identify whether that's a load of old people, or it could be Bangladeshi communities who we seem to be failing with this model. It doesn't do very well for that subgroup within the UK population. And can we then boost them by simulating that type of person within the data set? And it doesn't have to be one protected characteristic. We can actually put in a load of things. So it could be over 70-year-old Afro-Caribbeans who have a history of heart disease. Or it could be, you know, young people from this region in Southeast Asia. So you can be very specific and tailor how you boost your data sets. But again, what we're trying to do here is not just equalize stuff, we're trying to recreate, you know, the true distributions. And we could simulate this quite easily. So we could actually say, well, let's create a bias within the data set that wasn't there, and then see if our method will identify the bias and if the boosting will correctly correct for some of that bias. And this isn't that straightforward to follow, but it's exactly what we managed to do. So we have a biased data set in green. We have the uncertainty for all of these different subgroups of people, ethnicity, and then we've boosted them in different ways. So you can see that actually there was not much uncertainty. It's less for the white population, whereas for the Black Caribbean population, massive uncertainty for this particular classification task. I think this was atrial fibrillation. So it identifies who we need to boost. And then as we do that, we boost them. We can see our approach is correctly boosting that population and actually doing very little to the wide population. We have enough data to be able to make good classification models from them. So we better represent the underlying populations. And nicely, we also improve our classification statistics. So we get better accuracies when we boost, we get better precision, and we get better recall. So it's quite interesting that rather than just trying to balance our data sets, we're trying to create data sets that are more realistic. But as a side effect, we actually end up with better accuracy than just hardwiring in a 50-50 balance. So this is working quite well. We're extending this in a number of different ways, in particular, trying to really focus on particular diseases and how the UK has underrepresented parts of the UK population for specific diseases. So just answering that question is of great use to the Department for Health, but then also using boosting to help with that. So that's one key way of dealing with bias. Another way of dealing with bias, which is much trickier, is when the labels are biased, okay? And that's far less straightforward. And we haven't done any work in that yet, but there's a really nice paper that came out in the Journal for Machine Learning Research, which I think goes some way to solving this problem. And this is you identify a sensitive attribute, build a neural network model that's going to be responsible for classifying that data set, but also classifying the sensitive attribute. So here's a completely different example, okay? If you were to build an AI model, a deep learning model that has to recognize the difference between an orca, killer whale, and a cheetah, okay? You could build that model with loads of example images, and when it comes to classify it, it gets 99 or 100% accuracy. So it's getting the right decisions, but for completely the wrong reasons. It's not looking at the creatures themselves in the images, it's just going lots of blue, lots of green. If there's lots of blue, it's an orca. If there's lots of green, it's a cheetah. So it's making the right decision, but for completely the wrong reasons. We do not want decision-making within the NHS anywhere to be making the right decisions for the wrong reasons, because suddenly something could go really badly wrong on an industrial scale. So by building these models that kind of streamline getting good classification accuracy, but also predicting, so here the background, the blueness or the greenness, you kind of pull away that proxy for the classification and separate it out from the decision-making for the class label. So this could be a potential way for trying to extract potential biases in some of the healthcare for labeling different groups historically. So this is something that we haven't explored yet, but it's something we would like to explore. Okay, I'm now going to move over to Awad, who is going to talk about some other impacts of using this sort of large-scale data set when it's developed, when it's being released over time. So shall I just hand you that? And mouse.
Thank you, Alan. Good afternoon, everyone. My name is Awad Al-Said. I'm a PhD student at Brunel University. Actually, I'm so pleased for being here today just to present our project in Portal. So in the top of the bias problem, we found in, as Alan mentioned previously, we found there's a drift can happen over the data. So over time. So this drift can happen sudden, such as new measures, or can happen over time incremental, which is for age population of the data or lifestyle change, and it's called drift. As everyone knows, so the patient's data, patient data, medical data, all this is the behavior, the medical history is all stored as a data. Then this data can be used to train supervised machine learning model in order to predict clinical future. This is the future can help clinics to assess the patients. So if there's drift in the data, the performance of this is a supervised machine learning model will drop, and that can be drift. So, well, actually, in this case, we take action, update the model. So, well, at COVID-19, there's many AI models has been, the performance of them has been ruined, which is COVID periods, as everyone knows. So in this case, so if you can see here, this is, for example, how the data, well, actually, the concept drift means is the change. I just would like to explain about the concept drift. The concept drift means is the change of the relationship between the input variables and the target variables for maybe unseen, for hidden concept. So, and basically, in short, I can say what we are trying to predict is change. So if you can see here, this is, for example, how the original data distributed. And this is, for example, the supervised machine learning model, let's say. So where here, for example, the virtual drift, the input variables, the distribution of the input variables change, but still the target variables still not change. Where here, for example, the target variable, the distribution of the target variable has been changed, and that's kind of that affect the model performance. So basically, there is many type of concepts, such as sudden drift, where, for example, this drift can happen within a few weeks or few months. And one of the best examples, COVID. So within a few weeks, everything changed, shopping and etc. And there's another gradual drift and incremental drift. That drift, it's happening gradually incrementally, which is replaced, the data is, the new concept replaced the old one gradually, and this can take years. Where the last one is recurring concept, which is the data still the same, then concept happen, then after that, again, back to the old model. And this is, we can say, for example, some seasonal drift. Sometimes, for example, a model can work very well in the summer, but doesn't work in the winter, and other way around. So basically, the ability department, primary care data, so they're working on the patches. And they take decision based on the performance of the machine learning model, such as accuracy, sensitivity, specificity, precision, recall. If this is the matrix, if it dropped, this could be lead sign of the drift. So, but how we can detect drift? So we need, first of all, to detect drift. Then after the drift, we need to update. If there is drift, we need to update the model according to the drift. So there is many detectors. There is statistical methods such as DDM, drift detection method, and EDDM, early drift detection method, and time window distribution, such as pattern. So in this project, I was working myself on the established algorithm. It's called drift detection method. And I would like just to take the chance now to thank Pedro, because he was so supportive for me and was so patient by answering all my questions, just to understand how this algorithm works. So, well, this algorithm is streaming data, work with the streaming data. And basically, it just is monitor, after we build the model, it just monitor the error rate. So if the error rate decrease significantly, that means there is sign of drift. So it's based on the constant, it's based on the assumption that the error rate, so either stay steady or decrease when the new patient or new samples, they come in. So if the error rate is start increasing, that means there is a sign of a drift. They have two, in this algorithm, there's two alerts. So warning alarm and drift alarm, which is the warning alarm where the error rate of the sample plus the standard deviation of the sample, so will be bigger than the minimum, the lowest error rate has been recorded, plus 2 times the standard deviation, then your standard deviation. This is, in this case, if reach that one, that means there is warning alarm. Where the drift alarm, it's working on the same things, but it's going to be plus a 3. So, which is the error rate plus the standard deviation will be bigger than the lowest error rate to be recorded plus the 3 standard deviation. Well, in this is the algorithm. I managed to implement this algorithm in two data sets. So the first one was working in the cardiovascular disease, CVD. This data set was synthetic data. So it was about 90,000 patients. The patient was distributed from 2005 until 2015. So we tried just to make them within batches, annual batches. So as you can see here, so we couldn't find any drift according to the DDM. So which is the scale anyway, is very small. So wasn't any drift. I couldn't find so either drift or warning. So looks like that data set or our model is being stable in this data set. Basically, this was I just forgot to say. So we tried to predict death. So basically, if we try to predict something else, we might find drift. So what we are focusing on, it just is predicting death. So where the second data set, it was COVID-19. This is the real data set we be provided. So this is the data set that we managed to be monthly. So it was about, I think, 800 something thousand patients. So it was since the COVID started until October 21. So if you see the vertical line here, so that means there's drift. So first of all, when we build the model, then I just implement DDM. I found straight away there's drift on April. Then after that, I update the model according to that drift. Then I found another drift on May, where from May until February, the model was stable. I couldn't find any drift. When it comes to March, I found another drift. Then April was another drift. Then May. Then if you can see June and July, it was stable, and again was drift every month afterwards. So this is what we've done. Again, this is what we're trying to predict death. So if you try to predict different features, we might find. But what we are focusing in that project is just to predict death. So this is what my field in this project just was focusing in DDM, where Lena, she's now gonna explain the other approach, the new approach, and this we'll be working on. Thank you very much.
Thank you, Allan.
Thank you.
All right. Okay. Hello, everybody. I'm Millennium, and I'm working with them for some months right now. This is my first talk, so be kind with me. Right. All right. So as Alwan was explaining, he implemented DDM, which is an approach that in our case study came with some limitation, let's say. For example, it is very nice because it handles with streaming data, while instead we're handling batches of data. And also DDM algorithm is focused on error rate as metric to assess, while instead we were interested in a more flexible approach, which would handle different performance metrics, like wherever. So we came to a new approach, which is more flexible, let's say. And in this slide, I'm trying to explain our methodology with some figures. So what we did was we have our dataset, and we split our dataset in different batches, which could be monthly, could be annually, depends from the case study. And then we take our first batch of data, and through bootstrapping techniques, we obtain different samples. And from these samples, we train a model. So we have in the slide these 4 models. And then we use these models we test these models on the subsequent batches of data. So on train set 1, 2, 3, 4, for example. And from this test, we can obtain some predictions and then some performance metrics, which could be everything, could be error rate, could be recall, could be sensitivity, specificity, whatever you want. And then what we do is selecting our control set, which is basically our first test set. if we think about a new product on the market, which could be, for example, a new piece of software, it can be assessed, and then it came on the market with some performance matrix, which it must assure, So our control set is our baseline, let's say. And then we select the next batch in time, and we call it next test set. So what we did is to compare this distribution of matrix, because of course, from our four models, let's say, we obtain a distributions of matrix. We compare these two distributions. We use non-parametric statistical tests. We use, for example, Wilcoxon rank test, which is a non-parametric statistical test, which came also with an alpha value, which means the strong of the signal. So if the test says that these two distributions are significantly different, it means that a drift has been detected. So if a drift has been detected, it means that something in the data has changed, and we need to update our model. We experimented different types of updating. The simplest one was just to appending the historical data. So as we see, we just add a new batch on our training set, and we just move the control set and the next set, and we continue our procedure. If instead, if the test says that the drift has not been detected, okay, we keep our model, and then we just, we are happy with our model, and we just move the next test set, and we continue with the comparison with the control set and the next test set. And then, as Howard was explaining, we have these two data sets, with these two case studies, and we represent our results with this graph. So on the y-axis, we have our metric. This, for example, was an accuracy, while it came also with the confidence bounds. While on the x-axis, we have the time. So our batches, which are annually, if you see for the CVD dataset, the cardiovascular risk dataset, instead are monthly for the COVID-19 dataset. And as we expected, and also, of course, as Howard was saying, the vertical dashed line shows the drifts detected. So as we expected, the CVD dataset shows a very stable case study, and we only detect one drift. Instead, for the COVID-19 dataset, we obtain many drifts all over the place. Then we try to represent our results in a different way, and we call this validation table, which, according to me, shows nicely all the experiments we've done in this month. So this table each row represents a batch in time. So for example, this is for the COVID-19. So each row represents a month. Then we have a column drift, which let's say shows if we suspect that a drift has happened in that batch. So for example, for the COVID-19, we flagged the 2 national lockdown in the UK. We flagged when the vaccine came in, when the new variants came in. And then we run our model for different, we run our experiment for different models complexity, and for different matrix also, and also for different alpha values, which, remember, it was the level of significance of the test. And we obtain some kind of stability between different models, right? Another thing that we explore, coming back to the bias stuff Allan was explaining, was also, try to explore the concept of bias in the concept drift project, let's say. The idea was that maybe if you look at the overall population, you cannot find any drifts. But then if we instead have a look at, for example, some ethnic group, some particular ethnic group, you can find some drift there. So what we did is we train our model on all the data, but when it came to test it, we just focus on a particular ethnic group. And we applied this for the CVD case study because we already knew it was a stable case study. And what we found is that for the white population on the left, we see that the set of results is almost the same as the overall results. And instead, when we look only at the Bangladeshi population, we see on the right, we see drifts all over the place with this wide confidence bounds. We thought that maybe it was a matter of the size of the samples, of course, but it doesn't mean that it's less important. And also, we experiments on larger samples. For example, we split data by gender, so male and female, and we found the same kind of behavior. Right. Okay, to summarize, concept drift detection is impacted by many factors. It's a clear finding in this month from this project that many factors impact drift. So for example, the window size of the batches, so if it's monthly, it's annually, the model complexity, if you're using a registered regression of a neural network, which metric are you assessing? So if you're assessing AUC or if you're assessing accuracy, the difficulty of prediction tasks or the parameterization, so the level of significance of our test, but also the bias in the subpopulation. So a finding of this project is that if someone came up with a new product on the market and let's say a new piece of software, and to ensure the soundness of this product in the time, you need to check many factors like this one that I list. That's it.
Okay, thank you.
Thank you very much.
So thank you, Awad and Elenia. So this project, I should say as well, has been intense. It started in end of October, this concept drift component, and we have to have all our results in 2 weeks time, so to report back. And this is going to be impacting quite a lot of the regulation about how regulation will be updated if drift is detected. So really quite important. In fact, the team at the MHRA have started to advertise some of this work already and starting to prepare the health tech sector for regulation that's going to be coming in, using synthetic data, but also detecting bias and detecting concept drift. So it's been really exciting. It's been quite intense, but as a result, we haven't published anything yet on concept drift. We've not had time. It's all been about feeding these results through to the government, but the next few months, hopefully, will be much more about us advertising the work and publishing this work. So just to summarize what we've talked about today, firstly, synthetic data is clearly really useful in actually not just validating, but in developing models and validating models. Probably not good enough for the final release to market, but certainly good enough for companies and universities to develop models that are state-of-the-art and can then be validated with ground truth data within a government department. So these generative models clearly offer some promise in the way that they can handle many different types of data, time series, and so on and so on. But there's always that trade-off between utility and privacy. And we always, there may always be a risk that we will identify people, rare cases, rare disease, incredibly old people with particular types of rare disease, for example. And we have to accept some of those risks might be there. We've also seen how important bias is, and it's not just about underrepresented groups, but being able to identify those is obviously useful and the right thing to do. But there is potential for boosting techniques to overcome some of those. But also there's lots of other types of bias we need to explore too. And then concept drift is a major issue here. As we collect more and more data, as we store information about patients, whether it's in batch form or streaming, we have to accept that that data may change over time, and therefore the performance of the model or the model itself may change if it's automatically updated. And so governments have got to make decisions about how they regulate that. Do they accept that some drift is acceptable and fine, and that they just annually or every few years check for that? Or do they want something that's much more adaptive and almost real time, that they're constantly monitoring post-market these devices that are undoubtedly going to appear in the next few months and years? Okay, and lastly, there's 3 of us here, which is more than you normally get in a single presentation, but there's also some key figures who have been helping us on this. In particular, I should say, Pooja Miles in the centre, who works with the primary care dataset. She's the manager of all of the primary care dataset. She's been fundamental in pushing all of these different projects, but also Barbara, Namir, Juan, and Zenshin, who've been involved with many of the experiments that we've been talking about today. Thank you very much.